Dear students, so in this class let us discuss about location of a roots theorem in real analysis. That's an important result. Location of roots theorem. So the theorem states that let I equals closed interval AB be a closed and bounded intervals. F from I to R be a continuous function on I. And suppose that either f of A less than 0 less than f of B, or f of B less than 0 less than f of A. In either case, there exists a number C following open interval AB such that f of C equals 0. So this is the location of roots theorem. The theorem says that I equals closed interval AB be a closed and bounded interval. F from I to R be a continuous function on I, which is continuous function of I. If suppose f of A less than 0 less than f of B, or f of B less than 0 less than f of B, in either case, then there exists a point C which lies in between A and B such that f of C equals 0. How to prove this one? So the proof is in this way. I equals closed interval AB, which is closed and bounded. That means closed f of I. What is f? F from I to R is a continuous on I. So we know that by boundedness theorem, f of I is bounded. F of I is bounded. Okay. Now, if possible, suppose if first case is exists, that is f of A less than 0 less than f of B. If this exists, f of A less than 0 less than f of B, then what happens here? You can bisect the interval closed interval AB successively. Means let I equals closed interval AB. Okay, you can put a equals A1 and B equals B1. So we have an interval I1 equals closed interval A1 B. Enough. Let P1 equals A1 plus B1 by 2. Surely this P1 fall in where? P1 equals A1 plus B1 by 2 means P1 fall in I1. Agreed? P1 fall in I1. If f of P1 equals 0, what happens? So the result is immediate. If f of P1 equals 0, means there exists a P1 fall in or P1 fall in open interval A1 B1 or open interval AB such that f of P1 equals 0. If f of P1 differs from 0, what happens? If f of P1 differs from 0, then there are two possibilities. Either f of P1 is positive, or f of P1 is negative. Either f of P1 is positive or f of P1 is negative. Now, first case, if f of P1 is negative, what happens here? If, that's our first case, if f of P1 is negative, then what happens here? If f of P1 is negative. So, put P1 equals A2. So, for put P1 equals A2 and B1 equals B. Put P1 equals A2 and B1 equals or B2 equals. B2 equals B1. What is B1? B1 is actually B itself. put a P1 equals A2 and B2 equals B. So if f of P1 is positive, then put a P1 equals B2 and A2 equals A1. Okay. So in either case, so if f of P1 is positive, this one, and f of P1 is negative, you can choose P1 is in this way. Okay. So in either case, put I2. In either case, put I2 equals closed interval A2, B2. So what is P1? F of P1 is negative, then P1 equals A2. So here f of A2 is negative. Okay. If f of P1 is positive, put a P1 equals B2, then f of B2 is positive. F of A2 is negative and f of B2 is positive. Okay. So you can continuously bisect this process, the continuous bisection of this process. Then suppose that I1, I2, etc. There exist intervals I1, I2, etc. Ik, such that I1 superset I2 superset etc. superset Ik. Sure. Okay. Etc. superset Ik. And what about f of A2? F of A2 is negative. So clearly with the f of AK is negative and f of BK is according to this argument. Clear? Means if I2 equals closed interval A2 B2 with f of A2 is negative and f of B2 is positive. So you can continue this process. Means the bisection process of bisection. Then there exists the intervals I1, I2, etc. Ik. With I1 superset, I2 superset, etc. superset Ik. With f of, according to this argument, f of AK is negative and f of BK is positive. Then put on PK. PK equals, what is P1? P1 equals, we know that P1 equals A1 plus B1 by 2. So PK equals AK plus BK by 2. So PK equals AK plus BK by 2. Similarly, like this P1 equals A1 plus B1 by 2. P2 is A2 plus B2 by 2, etc. So PK equals AK plus BK by 2. If f of PK equals 0, then finished. Why? Because AK plus BK by 2 means PK. PK lies in where? Open interval AB, because IK is a part of this I. Clear? So PK fall in open interval AB with f of PK is 0. So you can replace this PK by C, f of C equals 0. Now, if f of PK differs from 0, what happens? If f of PK differs from 0, what happens here? When f of PK differs from 0, then continues this process. You can bisect this again. Okay. If the process terminates by locating a point Pn such that f of Pn equals 0, then the result comes. Means, if f of Pk equals 0, then the process stops here. Or that is our result. If f of Pk differs from 0, you can again continue this process. But after some step, we may assume the process terminates. When this terminates, this process terminates only after seeing a point Pn such that f of Pn equals 0. That's a first case. Again, there exists another possibility. If the process does not terminate, what happens there? If the process does not terminate, then we get a nested sequence of closed and bounded interval In. Okay. If this process terminates here by using or by with this property, then our proof is stops there. But if the process does not terminate, what happens there? Means the process is going on indefinitely. Then we get a nested sequence of bounded intervals In of length. So what is length of In? With the length of In equals Bn minus An. What is In? So here In equals An Bn. Okay. Then length of in is bn minus an. What is this bn minus an? Bn minus an is b minus a by 2 power n minus 1 by the nested interval property. Okay, this nested interval property is familiar with you. So, if this process does not terminate, means it is indefinitely going on, then we get a nested interval in with the length of in is bn minus an, that is b minus a by 2 power n minus 1. Why? What is length of I1? Length of I1 is b1 minus a1, that is b minus a itself. What is length of I2? Length of I2 is b2 minus a2. What is actually b2 minus a2? b2 minus a2 means it is b minus a by 2. Okay, b3 minus a3 means b minus a by 2 square, etc. So length of in is b minus a by 2 power n minus 1. Okay. Then by the nested interval property, there exists a point C fall in in. There exists a point C fall in in for all n means an less than or equals C less than or equals bn. C fall in in means what is in? Closed interval an bn. Therefore, C fall in in means C lies in with C ranges from where to where? an to bn. Clear? Then a less than or equals C less than or equals bn means, so it is 0 less than or equals C minus an less than or equals bn minus a. Clear? According to this one. C less than or equals 0 less than or equals C minus an less than or equals bn minus a. That means 0 less than or equals C minus an less than or equals, what is bn minus a? That is b minus a by 2 power n minus 1. Take limit on both sides. What I get? If you take limit on both sides, limit to 0 means 0 less than or equals limit C minus an less than or equals limit of b minus a by 2 power n minus 1. So, what is the limit of limit b minus a by 2 power n minus 1? This is always 0 itself. Okay, so it is limit 0 means 0, so 0 less than or equals limit C minus a less than or equals 0 means limit an equals C. Agree? So that is the result. Limit an, first result is limit an equals C. Clear? Now, again, if a less than or equals C less than or equals bn, again consider the next argument. If an less than or equals C less than or equals bn, so this means minus an greater than or equals minus C greater than or equals minus bn. If you multiply it throughout by negative, so minus an greater than or equals minus C greater than or equals minus b. So means, so that implies from here we have bn minus an, from here bn minus an greater than or equals bn minus c greater than or equals 0. Clear? What is bn minus an? It is b minus c. So b minus a by 2 power n minus 1 greater than or equals bn minus cn greater than or equals 0. Taking limit. What is the limit of this one? Means limit of b minus a by 2 power n minus 1 greater than or equals limit bn minus cn greater than or equals limit 0. The limit of this one, that's again 0. That means 0 greater than or equals limit bn minus, not cn, it is c. Limit bn minus c greater than or equals 0. So from here, what is limit to bn? It is limit to bn equals limit to bn minus c equals 0. That means limit to bn equals c. So listen, the second argument is limit to bn equals c. We already get limit an equals c. Limit an equals c. Limit to bn equals c means sequence an and sequence bn are converged to same point c. Okay. What is f? F is continuous on I. What is I? I is closed interval AB. So since f is continuous on I, we have f of an converges to f of c, and f of bn also converges to f of bn also converges to f of c. F of an converges to f of c, as well as f of bn converges to f of c. So that means, but f of an, what is f of an? What is f of an? F of an less than 0, f of an less than 0, and we already see that f of a2 in first case, or we already see that f of ak is negative and f of bk is positive. Okay, so in this case, here f of an is negative and f of bn is positive. F of n negative means what is limit f of n? So limit f of n is less than or equal to 0. What is limit f of n? That is f of c. That implies f of c less than or equal to 0. Again, f of bn greater than or equal to 0. F of bn greater than or equal to 0 means limit f of bn greater than or equal to 0. What is f of limit f of bn? That's again f of c. That is f of c greater than or equal to 0. So combines f of c less than or equal to 0 and f of c greater than or equal to 0. So combinedly we have f of c equals 0. That is what we recurse here. So that is the location roots theorem. Clear? If I equals closed interval a b be a closed and bounded interval, f from I to r is a continuous function, then if f of a less than if f of a less than 0 less than f of b, or f of b less than 0 less than f of a, so in either case f of c equals 0. This is the location roots theorem. Agree? Okay. Now let us consider another result, another theorem, that is Bolzano intermediate value theorem. Bolzano intermediate value theorem. Bolzano intermediate value theorem. So that's nothing but a corollary of the previous result. So here the theorem states that I be an interval f from I to r. F for I is nothing but an interval. So f from I to r is continuous on I, which is continuous on I, which is continuous on I. If a comma b fall in I, a and b fall in I, and k fall in r, k is any real number, such that f of a less than k less than f of b, f of a less than k less than f of b, then there exists c fall in I. There exists c fall in I such that a less than c less than b means c lies in between a and b, with then f of c equals k. Previous case, f of c equals 0 when 0 less than f of a less than f of a less than 0 less than f of b, or f of b less than 0 less than f of a. Here c lies in between a and b, and k fall in r with the f of c equals k whenever f of a less than k less than f of b. Yes. How to prove this one? So far its proof is, let a less than b, a less than b. If a less than b, then let g of x equals, let g of x equals f of x minus k. G of x equals f of x minus k. So what is g of a? G of a equals f of a minus k. Is it negative or positive? Listen, f of a less than k less than f of b. So what is f of a minus k? F of a minus k is negative. Sure. What is g of b? G of b is f of b minus k. What is f of b minus k? F of b minus k is positive. Clear? So it is when g of x equals f of x minus k, so this implies g of e less than 0 less than g of e. Okay, g of a less than 0 less than. So by the previous theorem, by the location roots theorem, there exists c following I such that g of c equals 0. What is g of c? G of c means f of c. That is f of c minus k equals 0. That means f of c equals k. Okay. Now, second case. If b less than e, then let g of x equals or h of x equals. Here, let h of x equals or g of x equals k minus f of x. K minus f of x. So what is g of a? G of a is k minus f of a. Okay, so it is k minus f of a. What is k minus f of a? That is positive. What is g of b? G of b equals k minus f of b. What is k minus f of b? That is negative. Sure. That means g of b less than 0 less than g of a. Again, by the location roots theorem, there exists c following a, b or I such that g of c equals 0. What is from g of c? Here k minus f of c equals 0. That means f of c equals k. So in either case, the result holds. So this is Bolzano intermediate value theorem. That is heavily depends upon the location roots theorem. Agree? Thank you.